Okay, so electrostatic potential. The governing equations in the charge-free region, the electrostatic potential V must satisfy Laplace equations, Laplacian of V equal to 0. So if we assume the potential only changes in one direction, the x direction, and is constant along the y and z axis. The equation simplify from a 3D partial differential equation to a simple 1D ordinary differential equations. So the partial of v with respect to x, the second partial of v with respect to x is equal to 0. So we have the derivation here. To find v of x, we simply integrate the equation twice. First, integrate both sides with respect to x here. So we have the integral of the second derivative of v with respect to x here equal to the first derivative here equal to dv over dx equal to c sub 1. So this tells us that the electric field is equal to negative dv over dx is constant throughout the region. So second integration, the integral of dv over dx times dx equal to, so is equal to c1 dx here, integral of this. We have the v of x here equal to c1x plus c sub 2. So this is the general form of any 1D Laplace solution, a straight line. So applying boundary condition to reach the specific solution here, v of x equal to 100x. So we must have a specific boundary conditions here. So at x equal to 0, the potential is grounded, v equal to 0. So plugging this in 0 equal to c sub 1 times 0 here plus c sub 2. So it means that c sub 2 here is equal to 0. At x equal to 1, the potential is 100 units. So plugging this in 100 equal to c sub 1 times 1 plus c sub 2, which is equal to 0. So we have the c sub 1 equal to 100. So substituting this constant back into our general form gives the general results v of x equal to 100x. So we have the physical interpretation here. So this linear result describes a perfectly uniform transition of potential. You have the uniform gradient here. Because the potential is a straight line, the slope electric field never changes here. No internal sources. Since there are no charges between x equal to 0 and x equal to 1, there are no bumps or dips in the potential. It simply flows smoothly from high voltage plate to the ground state. So we have here the uh, potential here, the electrostatic potential. So we have the electrostatic potential here is the height. We have the x and y. So this potential is a function of x and y. We have the contour here. So we can see the same potential here for this line. So the potential here is the same as the potential here. The potential here is constant. Then so we have the potential also here, potential along the line. So the potential here in the line, it has the same potential here. So from this point up to this point, we have the same potential. So the potential here is constant. Yeah. We have here the potential. We are going to increase the potential here. So we have the increasing of the potential. We have the electric field here. Electric field perpendicular to the potential here. So if we increase the potential, so we have also the corresponding change in the electric field. So this lets you change the plate voltage, say instantaneous in potential and electric field. So linear potential, it means a uniform electric field, no change. So for the Laplace equation, This is the canonical electrostatic benchmark. This is used in capacitor, uh, finite element method validations, PDE, or partial differential equation latching, and continuum and field theory. Field theory. So we have the electrostatic potential charge here. So we have the problem at x equal to 0. So the potential here is equal to 0. And if at x equal to 1, the potential is equal to 100. So we have the governing equations here. The second partial of v with respect to the second partial of the potential is equal to 0. So we have the v sub x here equal to 100 x. This is the solutions. Numerical value here, for example, if x equal to zero point 0.3, the potential is 30 volts. So the electric field here is negative 100. So we have the gravitational potential for the empty space here. So Earth, outside the Earth here. So the mass is 5.97 times into the 24 kilogram. So we have the governing equation here. The partial of the pi here equal to 0. So R here is greater than the this R is outside the Earth. So this is R is greater than capital letter R. So we have the potential here, negative of Gm over R at altitude 7 times into the 6 meter. The gravitational potential is given by this value, 5.69 times into the 7. The derivation of gravitational potential, the physical setup here, in a region without mass, the gravitational potential satisfies Laplace equations here. So this is mathematically identical to the charge-free electrostatic potential discussed in your earlier images. Because the mass is a sphere, we assume spherical symmetry, meaning the potential only changes as you move away from the center and does not change with the angles here. So the derivations, to derive the solution here, we use the spherical Laplacian. So simplify the Laplacian in spherical coordinates. The Laplacian of a function that only depends on R is. So this is equation that we derived before. Then first integrate to solve this. We multiply by R squared and integrate with respect to R. So we have here, so R squared times the derivative of the potential with respect to R here is equal to C sub 1. So this tells us that the derivative of the potential with respect to R, which is the gravitational field strength, must be proportional to 1 over R squared. So the second integration here, divide by R squared. So we have here the solution, the potential uh, as a function of 1 here is equal to negative C1 over R plus C sub 2. So we have the boundary conditions here. At infinity, R approaches infinity. By convention, we set the potential at infinity to 0. So this makes C sub 2 equal to 0. So the source constant here to match Newton's law of universal gravitation, the constant C sub 1 must represent the strength of the source. So we set C sub 1 equal to Gm. So substituting this back into N gives the final solution pi of R is equal to negative Gm over R. So we have the plot of this potential. So we have the zero potential here at this at the potential at 0 here, the function of x and the function of the phi as a function of x and y here. So this is the potential equal to 0 here. So we have the potential from a massive object here. For example, the Earth. The potential here at the center is uh, the potential here is um, maximum. So, for example, if we increase the value of x and y here, the potential decreases to 0. But the potential here at the source is equivalent to the singular point. So there is a singularity here at the center of the, for example, a star. There is a singularity point at the center of the star here. But for the Earth here, uh, R is not exactly equal to 0. So we have the small value for R here to approximate the value of the value of the potential here. But the potential at the top here is equal to 0 here. So we have the uh, increase of the potential as increase of potential as we decrease the distance here. Because the distance, the negative distance increases if the distance is uh, smaller. But if the distance is larger, but it is negative, it becomes smaller and smaller. But if it becomes, for example, if we decrease the magnitude here, for example, from -4 to 0, the potential decreases. Now, if decrease the distance here from 0 to -4, that decreases the distance. So that increases the potential of the planet Earth. Then we have the contour here. So for each uh, circle here, we have the same potential. For example, the potential at this circle are the same. So the potential here is constant, uniform. So we have the vector plot here. So uh, the gravitational field is directed towards the center here. And so we have the contour here. So we can decrease the mass at the center. And also we can decrease the universal gravitations. We have then we have the epsilon here. So the epsilon here uh it is to avoid the zero divisions, you have to introduce the EPS here because the EPS here is the distance here r is equal to the square root of x squared plus y squared. But we have to add the EPS to avoid the division by 0. So this lets you increase mass, strengthen the gravity. So we have the across the image, across all the images you have shared, you are looking at how a potential field, whether voltage, heat, or gravity, behaves when it's just passing through empty space. So we have the 1D plate here, the partial of v with respect to the second partial of v with respect to x here is equal to 0. So this is for the linear. For example, in our example, our typical solution here v is equal to 100x. And for the two-dimensional, the second partial of t with respect to x plus the second partial of t with respect to y equal to 0. And we have here for the spherical here, the Laplacian of the the Laplacian of the gravitational potential is equal to zero. So the solution here is uh, the gravitational potential is equal to negative Gm over R. So we have here the G is the uh, universal constant, the gravitational constant, and we have M here, the mass of the Earth. So in every case, the field is harmonic, meaning it is as smooth as possible and uh, dictated entirely with the boundaries of or the source outside the region of interest.